Hey guys, today we're going to take a look at the differences between ideal gases and real gases. So we're going to start by reviewing the assumptions we made in order to assume something was an ideal gas, and we're going to talk about how certain things might violate those assumptions. So let's go ahead and get started. Now, if you remember that with an ideal gas, we assumed that the molecules of gas themselves take up no space. We also assumed that every collision was perfectly elastic, which means that no energy would be lost when either molecules bumped into each other or molecules bumped into the wall. And we also assumed that the molecules themselves didn't interact with each other. So they didn't attract to each other or repel each other in any way, shape, or form. They just kind of existed. All right? Obviously, those are assumptions. We call those assumptions, which means that must be a violation in some way, shape, or form of those assumptions. That's what makes a real gas real, is it in some way, shape, or form violates one of those assumptions. Now, one of the ways we applied the ideal gas behavior was within our ideal gas law. Additionally, if we see violations of ideal behavior, we can actually see an impact on our calculations in the ideal gas law. There's a manipulation of the ideal gas law called the Waals Equation that tells us how each of those assumptions being violated could impact the overall ideal nature of a gas and thereby quantitatively tell us how it impacts the pressure and the volume of the gas that we're going to observe. So there are two assumptions in particular that we focus on being violated within the ideal gas law, and that is going to be the fact that the molecules themselves don't take up space, which in fact they do. As matter, they both take up space and have mass, so that's a critical violation. And the second violation is that the molecules don't interact with each other. Now, we haven't gotten to the part of the year yet where we talk about the interactions between molecules, but I'm going to introduce that to you today to at least give you some context that we can apply to this violation. So let's look at the first violation of an assumption. The first violation we're going to focus on is that of attractive forces. Now, molecules, as they move past each other in space, in some circumstances are going to attract to each other. Kind of like two magnets, if you move them across each other, they might have a moment where they're attracted to each other. That's not always happening, but it does when they come into close proximity. Now, when that happens, it's going to slightly slow down the movement of those molecules past each other. So slowing them down. That's going to violate one of the assumptions of the ideal gas law, in that molecules aren't moving in straight lines and aren't interacting with each other as they move. So the idea here is as those molecules move past each other and they interact, they slow down. In terms of kinetic molecular theory, what this does is it impacts the overall observed pressure. Well, think about it. How? If we're in a circumstance where molecules start slowing down, then the rate at which they hit the walls of the container, it decreases a little bit because they're taking some time to interact. Now, if we are going to look at the ideal gas law and see a violation here, the way we see this violation is going to be a slight change to the observed pressure. What this means is that the real pressure is going to be slightly less than the ideal pressure. So if we look at how this affects our equation, going from an ideal equation to a real equation, so the van der Waals equation, is we have to correct for this idea of attractive forces. So if we look at the equation manipulation, we're subtracting from the ideal pressure that we would have seen in order to get our real pressure. The attractive force can vary. Some molecules would be more attracted to each other, others would be less attracted to each other. In the case of gases, the more polar a gas is, so remember back to biology, you talked about polarity of water versus non-polar substances like fats and lipids and waxes, right? The polarity of a molecule impacts how much it's going to be attracted to other molecules. The more polar the molecule is, the more it's going to be attracted to other molecules of the same type. So we correct for this by taking the attractive correction away from the ideal pressure, and that gives us our real pressure. The second assumption we are going to look at is the correction for volume of a molecule. If you think about it this way, if I took gaseous water, so water vapor, and I cooled it down, what happens? Well, some of that water condenses into liquid water. But liquid water has volume. We know liquid water has volume. That means the molecules themselves of water have volume. We can't ignore that in a lot of circumstances when we're talking about a gas. Now, an ideal gas, we assume the molecules themselves took up no space, and that's simply not true. So when we think about volume of a gas, really what we're thinking is the distance between the nuclei of two different molecules of a gas. But in a gas that takes up space, now the atoms or the molecules themselves, they take up some of that space. The bigger a molecule is, the more space it takes up, the more this assumption is going to be violated. So a violation of this assumption is going to impact the observed volume of a gas. Why? Well, it's because there's volume present that we aren't accounting for. In other words, the bigger a molecule is, the greater the observed volume will be compared to the ideal volume. Now, if we look at how this is going to manipulate the actual ideal gas law equation, here what we're doing is we're correcting for the true volume of the molecules. So we have to add the true volume of the molecules to the assumed ideal volume that we would have calculated, and that's going to give us our real volume. Now, you're not going to have to use the van der Waals equation quantitatively, but you will need to understand how certain things can violate the ideal gas law and in what ways. So you need to know if the pressure is going to be too low compared to what you would have expected, or if the volume is going to be too high compared to what you would have expected. And in addition, you're going to need to know under what conditions are they going to violate more frequently. So let's talk about the conditions under which the ideal gas law is more likely to be violated. Temperature is a critical factor in any substance. Of gases especially, as the temperature increases, so does the velocity at which any of those molecules move past each other. Think about it this way. If you are late to class and you're running down the hallway as fast as you can, even if you see your best friend in the hallway, the time in which you have to interact with them is very, very limited. So you're basically going to sprint past them. You might shout a hey, but overall, it's not going to slow you down. However, if we're moving slower, maybe we're casually walking down the hall, right? You're just going from the bathroom back to class. You got no interest in going back to class. So what you're going to do is you're going to take your time. Oh, you see a friend in the hallway. Let me talk to them for a little bit. Let me have a conversation. Now all of a sudden, because you were moving slower to begin with, you had more time to interact, and that interaction had a greater effect. This is the same in molecules. The faster the molecules are moving, the less the interactions between the molecules matter. So even a very polar molecule might not violate the ideal gas law at a high temperature because of the fact that they're not going to have the time to interact with others. Now, the slower molecules move. This would be at low temperatures. Now all of a sudden those interactions matter. So the ideal gas law is more likely to be violated at low temperatures than at high temperatures because of the increased opportunity for molecules to interact. Additionally, the ideal gas law is more likely to be violated in circumstances where under very high pressure. Why? Well, under high pressures, what's going to happen is the molecules by their nature are going to be colliding more frequently with the walls. And the reason for that is because there are just more of them in that certain region, in that volume. So in other words, you can almost think of this as proximity to each other. So under high pressures, molecules are much closer to each other at any point in time. Well, that's like having a circumstance where you have a room packed with people. If I've got people all throughout the room, the amount of air in the room is substantially less because I exist in the room. So I'm a solid. I am a thing. I don't have air, well, not a lot of air, in my body, and as a result, I take up volume that otherwise would have been occupied by a gas. Molecules are the same way. If you pack molecules in tighter, then there's more violation of the ideal nature of the gas because of the fact that the molecules themselves are closer together. The volumes that they make up, right, the actual molecules themselves, the nuclei and their electron shells, they are going to make up enough volume to impact the total volume that you are going to observe overall. So, the ideal gas law is violated more often at high pressures than at low pressures. So, here are the ways the ideal gas law can be violated. Number one, if a molecule is more polar. Number two, if a molecule is going to be larger, or an atom is going to be larger. 3, at very low temperatures, when molecules aren't moving nearly as fast. And 4, at very high pressures, when you have more molecules of gas packed in together. Under those four circumstances, we will see violations of our ideal gas law. So let's look at a practice problem. In this case, we have molecules of helium and molecules of xenon. And I want to know which of them would violate the ideal gas law more than the other, right? In the ideal gas law, we're going to look at those 4 things again: temperature, pressure, polarity, and size. Well, in both of these, the temperature and the pressure are the same number of molecules of gas, same container, same temperature, all of that. Where they differ, however, is going to be in the size. The size of these 2 atoms. So helium is much, much smaller than xenon. So the volume that a helium atom makes up is extremely small compared to that of xenon. Therefore, if you look at the xenon atoms, they're going to violate the ideal nature of their gaseous state more than the helium because of the fact that they are larger. What this is going to do is it's going to make your total volume that you observe greater than you would have predicted using the ideal gas law. Because again, we'd predict that helium and xenon would take up the same space, but they don't. Xenon takes up more. Now in this next one, what I'm doing is I'm taking the same sample of nitrogen, and I'm simply decreasing the temperature. And what's going to happen here is as we decrease the temperature, I want to know how the real pressure is going to vary compared to what we would expect given the ideal pressure. Now, if it was an ideal situation, we would expect that as we change the temperature, the change in pressure would scale proportionally. But in this case, that's not going to happen because the temperature gets so low that even nitrogen is going to end up exhibiting a deviation from its ideal nature. So nitrogen, as it starts moving slower, is going to start interacting with other nitrogen molecules. So what's going to happen is they're going to slow down even more than you would have predicted just by the change in temperature. This is going to change the pressure to become even less than you would have expected it to be based on the ideal behavior. So again, low temperatures, you're going to see a deviation from ideal behavior because the molecules are going to interact more with each other. So that wraps up today's video. Let's do a quick recap. Today we talked about how real gases can deviate from the ideal gas law, and we talked about the 4 circumstances under which they do. Whether it's at low temperatures, high pressures, with gases that are more polar, or with gases that are going to be made of larger molecules, right? So those are the things that are going to deviate from our ideal gas law, and we then discussed using the van der Waals equation, which remember you don't need to know quantitatively, just qualitatively. We discussed how that's going to impact our observed values for pressure and volume compared to our expected values for pressure and volume. I'd like to thank Saula Zaprowskis, Hunter Lee, and Amy Lambert for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.